the problem here is coming from example 22.6 in the 10th edition of the book, and so it's already been solved fully, but I wanted to go through it a little slower because I know sometimes it can get overwhelming when you see all of these equations that you can't really make sense of. So the question is asking us to find the components of the net electric field at point P. So here, this is our configuration where we have a positive charge here, right? And we have a negative charge here, and we want to know what is the electric field way down here. Now, the interesting thing to note is that they are not evenly spaced, right? So this is the center axis, and this one is position, the distance is A away. Here it's B away, so they make different angles, and we're going to have some weird looking net electric field. So the first thing we can do is visualize what's happening. What I mean by that is to pretend like we have a positive charge at point P and see what would happen to that positive charge. Now, here we have positive and positive, so it's going to be repelled along this axis. So we follow this axis, and it's going to be repelled this way. And this is going to be our electric field due to charge 1. Now, if we have a positive charge here, and we have the negative charge down here, it is going to feel an attraction along this axis towards the negative charge. So our net electric field is going to be somewhere in the middle of these two. And here we see that it's pointing along there. Now to actually figure out where exactly it's pointing, we're going to have to use our equation, which hopefully you remember. So E1 is equal to KE, so this is the magnitude of E1, is equal to KE Q1 over R1 squared. And this is for finding the electric field of a point charge, right? So this is the electric field E1, its magnitude. It's going to be KE Q1. We don't know what Q1 is, it's just a number for us right now. And then how far away is it? So that is going to be R1, right? And so we can just use the fact that this is A, and we know that this here is Y. We're told that. So here we have A squared plus Y squared. Square rooted, but then also squared, so we can just leave it like this. Now the magnitude of E2 is going to be equal to KE Q2 over R2 squared, and we look at what R2 is, and we see here that we have B and we have Y, so we do the same thing, and we have KE Q2 over B squared plus Y squared. Okay, so the next thing to do is find where E1 is pointing. And the first thing we do is we have the magnitude, right? We already know this. And then we look at its angles. What I mean by that is we know that E1 here is going to be pointing in this direction, and we know it's going to be making an angle phi with the horizon, because right here is following this path, making this angle phi. So when we want to find the x component here, this is going to be the cosine side, and this is going to be the sine side, because again, this is the opposite and this is the adjacent side. I'm going to put that together and say, okay, well, it's going to be cosine phi in the I hat direction and sine phi in the j hat direction. We're going to do the same thing for E2. So E2 has magnitude of KE Q2 over B squared plus Y squared, but where is it pointing? And we see that here it's actually pointing down, right? So sure, it has a positive X direction, but has a negative Y direction. And we do the same thing where here, this is the sine side, and this is the cos side. So I add all those together, and we have cos of theta in the I hat negative sine of theta in the j hat. And this negative sign is, of course, really important because it is going downwards, right? Now the next thing to do is just add up these x components, add up these y components, and end up with a net electric field vector. So the x components are going to be just KE q1 over a squared plus y squared cos phi plus ke q2 cos theta over b squared plus y squared. And our y component is similar, ke q1 sine phi over a squared plus y squared minus ke q2 sine theta over b squared plus y squared. There's really no point in going any further than that for this part of the question, right? Now, if you go into the example, there's actually a part B, and B asks us to evaluate our electric field at point P when Q1 is equal to Q2 and when A is equal to B. So let's see what that will look like. Now, if these have the same magnitude of charge, that's easy because there's then no distinction between Q1 and Q2. So this is Q and this is Q, and then there's no such thing as 1 or 2 because they're the same. And then here, A and B are going to be the same, which means they're going to make the same angle, right? So this angle here is going to be the same as this angle here. And what we're going to notice is that if I erase this stuff here, we're going to have an equal amount going up like this and down like this. And our net electric field is going to actually end up pointing straight out along the x-hat direction. And we can see that mathematically, right? So if we have that, phi is equal to theta, A is equal to B, Q1 is equal to Q2. Then we have, okay, well, we can just look at it here. So then if this is the same, this becomes theta, right? Here I'm just going to erase Q1, Q2. Just going to also erase this because they're all the same now. So here it's just Q, Q, A, right? So here KEQ over A squared plus Y squared cos theta plus the exact same thing gives us 2 KEQ cosine of theta divided by A squared plus Y squared. Now for this one, same deal. This just becomes Q, this just becomes Q, this is sine of theta, and this is A squared. And what we see here is that we have KEQ sine theta over A squared plus Y squared minus the exact same thing. These cancel out and we're left with 0. So when we have this configuration, our net electric field is going to be 2KE QA over, I shouldn't skip steps. It's going to be 2KE Q cos theta over A squared plus Y squared. There's one more thing I can do. I can define what cos theta is as being A divided by R if I go back up here. So the cosine of, well, if this is theta and this is theta, the cosine of it is going to be A, so whatever this is, right? And this is R, and this is R. Is A over R, and we know what R is, right? So it's going to be A divided by square root of A squared plus Y squared. And so we're going to get EX is equal to 2KEQ A divided by, and then here we're going to multiply this by this, which is going to give us A squared plus Y squared to the power of 3/2.